Okay, can you all see my screen?
Perfect.
Okay, so good morning, everyone. My name is Maxime Joss, and I am a postdoc at UCSB. And as Norm says, I'm going to introduce a few concepts on how to implement neutral atoms as qubits for a quantum machine. And I will focus on a very limited aspect of the very broad quantum project, which will be the physical implementation, namely the hardware. And later, Dan will talk from higher level aspects of this project, namely the different applications, quantum simulation, and computation. So I will start by introducing the neutral atom as a qubit, then illustrate how is it possible to scale up to more than 1 qubit, and then briefly mention the different interactions that you can have between atoms and the way we detect and read out qubits. Let me first recall that there is other promising candidates and atoms. Maybe the most famous one is are the superconducting circuits. Last week we heard about ions. I personally work on defects in solid. There is quantum dot. All of these candidates have strengths and weaknesses. Maybe the clear strength of neutral atoms is the very long coherence that you can achieve. So I will try to motivate now on this slide why we need to go to cold temperature. So there is plenty of good reasons to go to cold temperature. This is just one point of view, maybe a little bit restrictive, but okay, this is the story that I want to tell on this slide. So here's a typical energy diagram of an atom that consists of an infinite number of discrete energy levels. And generally, the qubit is just encoded on two very stable states in the ground state. And in order to prepare, manipulate, and detect this qubit, we need to go through an optical transition that couples its ground state to an excited state manifold here. And these are the typical energy scales that we have. And if we want to have good preparation, manipulation, and detection capability, we need to have very high spectral resolution on this transition. And typically, what we want to aim for is a few megahertz resolution. And due to the Doppler broadening, the fact that atoms fly around at very high speed, that completely blurs the spectral lines, and that makes spectroscopy very hard. So we need to cool down the atoms, and basically what we aim for is typically below 1 megahertz resolution, and that corresponds to around 1 nano EV, and that corresponds to a temperature of 1 millikelvin or even lower. So we need to go to low temperature, and for this reason, we need to trap and to cool. These two things are often related, come together. So how to reach low temperature? First thing is that you have to isolate your atoms in an ultra-high vacuum environment, especially to prevent very fast atom to hit the atoms that you want to cool. And you need to apply different techniques of laser trapping and cooling. So this is how a typical a quantum machine looks like. So it's typically 1 meter by 1 meter. This is the scale. We have here, for example, the science chamber in the middle with different optical axes for the laser to go through to manipulate the atoms. And this chamber is made of steel in order to have very high vacuum. We have pumps all around the chamber to reach a very low pressure. And we have here, for example, an atom source that fires atoms at room temperature or even higher. So we have to slow them down and bring them already slowed down to the chamber. So this is just the chamber. Then often you have next to this, you have a lot of laser preparation and dedicated table. So I described very briefly 1 qubit. Now we want to scale to n qubit. That means we want to place the atom, the qubit, in a structural lattice with the desired geometry. And the desired geometry depends on what we want to do. If you want to simulate, if you want to do quantum computation. But usually the common approach is to integrate the atoms using an optical lattice, or equivalently optical tweezers. So here you have an example of an optical lattice with a special Kagome structure. And these are another kind of array of atoms that you can have with optical tweezers. So I'm going to spend a little bit of time on this particular way to arrange the atoms. This relies on what is called the dipole force within the dipole trap. And one implementation of the dipole force is the dipole trap. And so the magic thing about the dipole trap is that it doesn't rely on radiation pressure. You can apply forces on atom with laser light without exciting the atom. And to achieve this, you need to be far detuned from the resonance of your atom. So the key mathematical formula is that the potential of created by this laser field here is proportional to the intensity of the laser. And the typical depth of trap that you can create with laser dipole trap is, well, the depth is on the order of 1 millikelvin, and you can trap for typically seconds. So it's very important to understand the relation between the potential of the trap and the intensity. And the proportional constant here has to do with the real part of the polarizability, but basically the amplitude of alpha here tells how efficient your trap is. So how deep is the trap for a given amount of optical power. And the typical power that I use to have around 1 millikelvin of trap is typically 1 milliwatt. So this is to trap 1 qubit, 1 atom. So if you want to trap, let's say, 1,000 atoms, you will need 1 watt of power. And that starts to be not as trivial. Finally, the sign of alpha, as I will describe on the next slide, actually, the sign of alpha defines if the trap is an attractive trap or a repulsive trap. And finally, you have to, the figure of merit here in this kind of trap is really how deep is the trap compared to the residual kinetical energy of your atom. And in this kind of trap, the residual energy has to do with the recoil energy. That is the kinetic energy that an atom acquires when it absorbs a photon. And the typical order for this recoil energy, expressed again in terms of temperature, is on the order of 400 nanokelvin. So these dipole traps has to be higher than a few hundred nanokelvin. So now I'm going to describe in more detail this dipole force that enables to trap atoms without exciting the atom. And I'm going to use a totally classical model, which I absolutely love, which is called the Lorentz model, and that describes the atom as an electron elastically bound to a positive nucleus. And we put this atom into a gradient of intensity, which corresponds also to a gradient of electric field. So here you have, for example, the atom in a laser beam. And what we want to show here is that this atom is going to be attracted toward the high intensity region of the laser beam. So I plotted here the electric field near the center of the beam, which has a high amplitude, and here the electric field near the edge of the beam, which is of smaller amplitude. By the way, Norm, tell me about the time. I am out of training on this.
You have about 7 minutes left.
Yeah, that should be good. So, so what happens when an electron is subjected to an electric field? It has a force. And in this particular case, where we use a very low frequency for the laser field, the electron has time to catch up to this field and will basically oscillate in phase opposition with the field. But when it will be pulled toward the higher field region, it will be pulled more than when it will be repelled here. So that little by little, the electron will kind of drift toward the high intensity region, the high field region, and will drag, so to say, the atom toward the center of the laser. So this is when the driving field is slow. That in fact this electron is elastically bound to the nucleus, so it is an oscillator. It has a resonance frequency, and if, for example, you drive the system with a too fast frequency, so that the electron cannot catch the driving field, it will actually oscillate in phase, and then you will have the reverse process, namely the field will little by little push the electron out of the laser beam. And so that's why, depending on the laser frequency, if the laser frequency is smaller than the atom resonance frequency, you have an attractive force. And when the laser frequency is higher, you have a repulsive force. So you have really this degree, this wonderful degree to control the trapping of the atom. So now I will briefly mention the different interactions among atoms, because you need to have the atoms interact once you have put them in this lattice structure. You need to have them interact and doing the quantum operation that you want. And maybe this is actually, it's time to mention that maybe this is the weak point of atoms, of neutral atoms. They basically don't interact very well, especially when they are a few microns apart, as it is the case on optical lattices. So here, for example, dipole-dipole interaction, typically interaction strength is on the order of 1 Hertz. There is other exchange interaction, contact interaction, and maybe the biggest and the significant step that we can use with neutral atoms is to promote the atoms to Rydberg states. So basically, it makes the atom very big with a large dipole so that it can actually interact on micro metascales and reach really nice interaction strength, interaction energy. Final slide is to mention the different detection in order to observe and read out the atoms. The two main techniques are absorption imaging and fluorescence imaging. And absorption imaging just relies on imaging the shadow left by the atoms when you shine a laser beam on it. This is probably the most popular absorption imaging I can think of is just the interference of matter, the interference of two DECs. And finally, you have also a very sensitive technique called fluorescence imaging, which works similarly, except here we measure the scattered photon instead of just their shadow. Yeah, so that's it. I think I covered a few aspects related to the hardware of atoms, of cold atoms.
Perfect. Yeah, thanks so much, Maxime. That was really wonderful. Did you want to introduce Dan for his talk as well, or?
Well, I can go until to the fellow and awards and this kind of thing, which I don't understand.
I think it's okay. I think in that case, I think Dan would appreciate the extra time anyways. I think we all know Dan, and if anything, I think one can look on any number of websites where Dan is the director of the CIQC. So maybe I would suggest then in that case, let's just welcome Dan to give us kind of a broad overview of not only of research, but also where he sees the center going and the role that the CIQC plays in the broader landscape of kind of quantum computing and quantum science. So welcome, Dan.
All right. Can you hear me?
Perfect.
Okay, great.
And we can see your slides.
Let me get a pointer. Yeah, so Norm, I thought you were going to say, I mean, we know Dan well enough, maybe too much. It's a very generous way of introducing me. Well, this is, I must say that, let me hide these controls just a second. How do I hide the bar? Okay, great. This is like the realization of a long-standing dream for me. So a few years ago, I felt like I just wasn't getting enough attention. And I wondered, how can I get more attention? So I came up with this idea that I would pull together a bunch of people and spearhead a proposal and bring in a $25 million center. And then I could invite myself as a colloquium speaker as part of that institute. So this is really like a dream come true. Thanks for participating. One bad thing about giving talks on Zoom is I have no idea whether anybody's laughing. So I'll just keep going with my jokes. Okay, so the other day, now that we're in the world of quantum computing as established by the foundation of this center, I figured I should maybe buy myself some quantum computing hardware. Everything these days is delivered, by Amazon or some other remote shopping to the house. So this is the box that came from QTech, and when I opened it up, you can imagine my disappointment and surprise to find that it was completely empty. But then I decided to turn lemons into lemonade, and so what I did is I bought myself a really great microscope objective, and I set up a couple of laser beams that are close to some atomic resonance. And like, lo and behold, I found that actually this box was full of lots of extremely high quality qubits. So here's a picture of a few of the qubits that I snagged when I opened the box. These are, I'll talk about them in a little bit. These are actually images of single rubidium atoms that are trapped in one of these tweezer traps that Maxime nicely described. And they are constantly fluorescing light, which is also laser cooling them at the same time. And one can just set up a standard camera and see them glow. They stay fluorescing for on the order of 50 seconds or so before they get knocked away by some background gas atom. These qubits are, these atoms are amazing because they represent completely identical and perfectly constructed qubits. There's no tuning or fine tuning required to make their resonances match up. They just work one like the other, just straight out of the box. And their ground states in which you might store quantum information are as long-lived as you would care to study. I think the hyperfine ground states in rubidium have a half-life of, again, spontaneous emission of about 400,000 years. So that seems long enough for us to do our calculations. So, so the messages that came into this box is that there was a little slip that said that ultracold atoms are actually potentially a tremendous resource for lots of what we want to pursue in this kind of new era of quantum mechanics. People call it quantum 2.0, but it's sort of getting more serious about controlling quantum mechanics at a deep level, understanding it deeply with those kinds of experimental controls that we have, and then also maybe turning it into some kind of useful hardware and devices. What my research group and I specialize in is delivering on that promise to use ultracold atoms as our vehicle to study study the quantum world. And this field blossoms. It drinks, its roots drink from many decades of fundamental progress in atomic physics. Since the birth of quantum mechanics, which gave us ultimate control over the internal state space of atoms and lots of the basic ideas by which we understand coherences in quantum systems and how to manipulate them. Now, to let this nourishment rise into the current era, there was also a lot of foundational work on techniques which would not just control the internal state space of atoms, but also control their center of mass motion, so their external state space, if you will. And methods like laser cooling and also evaporative cooling, trapping techniques aplenty involving either magnetic or optical or sometimes electric fields, ways of controlling light atom interactions at a very fundamental level. All these kinds of basic techniques have led now to a field which I think of as a tree that is blossoming on very many branches. And along those branches, we see lots of really interesting science emerging. So, for example, one of the directions that's common in ultracold atomic physics is to create what are essentially material systems that are made up of collections of ultracold atoms that interact with one another and that mimic a lot of the properties that we see in condensed matter physics. Another essential direction in atomic physics is to use this new resource of highly coherent, extremely cold matter as a method to make precise measurements for both fundamental reasons and also technological uses. There's been some really lovely experiments in the last 20 years that touch on really foundational questions in few body physics. So cold atom systems can be made into 2-body, 3-body, 5-body, 10-body systems in a very controlled manner. And that allows us to study at a real sort of quantum state to quantum state level to study a lot of processes that should occur in few body physics. Ultracold atoms as a material also have a really unique property that, unlike materials which equilibrate rather rapidly to a thermal background, cold atom materials are trapped in relative isolation, and they can be driven into very far from equilibrium quantum dynamics. And that's just interesting for us to finally have a glimpse into at an experimental level. And then finally, and that's the theme of the Challenge Institute for Quantum Computation, is to develop all these ideas and channel them toward quantum information processing. Or here's another way sort of to organize the full space of what quantum 2.0 might be made to represent. Here's at least the European view of things, which is that on top of a foundation of basic physics science and computer science, there's going to be the establishment of various pillars for quantum technologies to make impact in the future in the area of communications, so sending qubits or codes around, computation, of course, trying to exceed classical computers, simulation, which is understanding quantum systems by representing them with other quantum systems, and then sensing and metrology, which is looking at fundamental aspects of nature, but also making more precise measurements. And cold atoms have a role in all of these pursuits. So my group and I have been working for years in this direction, and I should show you who the group is. Here's what a group meeting looks like recently. You see everybody's very happy because people are very happy in atomic physics. And but here's what I want to cover in the talk. I'll give some sort of touch points in my group of some of our efforts in the area of quantum simulation and quantum sensing, and then some of the directions that we're establishing toward quantum information processing. And I will probably, go through with too little detail to satisfy many of you, but I thought at the opening of an institute, it was important to give kind of a broader overview of what sort of is on the table. Okay, so let me touch on the first topic, which is quantum simulation of materials. And in particular, I'll talk about experiments where we investigate effects having to do with the band structure of important materials. So in condensed matter physics, and actually particularly at Berkeley, there's a lot of interest in certain types of materials. One of them is a class of materials known as Dirac and more recently Weyl semimetals. Here's a picture, for example, of one of these Dirac semimetals. It's a sheet of graphene. And I love this picture because you can really see the lattice structure directly and essentially in real time within this image. And graphene is interesting because starting from a foundational knowledge of its band structure and particularly a Dirac point within its band structure, which I'll talk about in a second, one derives a lot of really fascinating materials properties. And within a sheet of graphene, experiments can basically probe those phenomena directly, which is quite exciting. There's another class of materials which is wildly interesting these days, which are flat band materials. So materials in which the band structure is such so that many electrons have exactly the same kinetic energy. And the importance of that is that now interactions among the electrons cause the material to adopt a state of matter which is not trivial. So here's one example of a flat band material, which is twisted bilayer graphene. Here's images of it taken by Mike Cromie's group. And one of the features of this twisted bilayer graphene is that at a particular angle of alignment of two graphene sheets, one flattens out the band structure to a very high degree, and that allows something interesting to happen. So cold atom systems can be rigged up to study the underlying reasons for all of the interesting properties of these materials. So we construct optical lattices. As Maxime mentioned, we do this by taking laser beams and at the intersection of several laser beams, creating an intensity pattern of light where the atoms are attracted to certain locations, and those locations are periodically arrayed in space. So those locations can form, let's say, a honeycomb lattice coordination. I'm talking about two-dimensional lattices. Or also in our work, we often work with something called the Kagome lattice. And these two lattices allow us to get to the heart of these two types of materials. So for example, in the honeycomb lattice, if we look at the band structure in the lowest energy bands, we see that there's two bands that intersect at a point where there's actually a degeneracy between the two bands. These points are known as Dirac points. And the behavior of energy states near the Dirac point is what determines the property of graphene sheets. Similarly, relatedly, in the Kagome lattice, if we look at its band structure, we see that there's 3 low energy bands, and the third of them, when the lattice is sufficiently deep, is flat. It has 0 dispersion. All the states within that band have exactly the same energy. So working with these 2 lattices, we can study the physics of flat band materials or the study of Dirac points and graphene sheets. I'm going to focus, just because we're short on time, I'll just focus on the example of the honeycomb lattice and highlight some of the very recent work coming out of the group. Just by way of a touch point with the experiments are done by taking a gas of cold atoms. We work with rubidium atoms in this case, cooling them down to extremely low temperature. And in fact, the atoms are Bose condensed so that they macroscopically occupy the very lowest energy state of motion inside of our trap. And then we turn on these laser beams. So these are a set of 3 laser beams, or laser beams coming in from 3 dimensions that lie in a plane and intersect at equal angles at the location where the atoms are held. And these laser beams, we use actually a 2-color optical lattice. So one lattice is established by light with a long wavelength, and another optical lattice is established by light at a shorter wavelength, where these 2 wavelengths are exactly in a 2-to-1 ratio. The specific lattice that the atoms experience has to do with the specific interference between these laser beams, and we use interferometers to set that interference to have the specific pattern that we wish. With this kind of method, we can make a wide variety of lattices that all have a basic triangular form, but which have unit cells within this triangular lattice that differ from one another. So for example, in this diagram, if I just show you the lattice that's produced by this light at 1064 nanometers, the long wavelength light, it produces an intensity pattern, which is shown here. And this is light that attracts atoms to the regions of highest intensity. Atoms specifically find themselves attracted to the sites of a honeycomb lattice, which is akin to graphene sheets. In this case, the lattice spacing between neighboring sites is a few hundred nanometers rather than, let's say, a couple of angstroms like in graphene, but otherwise the physics of itinerant particles within the lattice should be the same. If we sent in just the green light instead, and we used it to establish an optical lattice, then we would make a triangular lattice. So if we want to study triangular lattices, here's our vehicle for doing so. Atoms would be attracted to all the spots where the laser intensity goes to 0. Or if we turn both of these colors of light on at the same time and we position them properly with respect to one another, we get a combined optical potential, which is shown here, which has the form of a Kagome lattice. So that would be the lattice in which we can study flat band physics. But I will focus actually just on experiments performed in this infrared honeycomb lattice that have to do with a Dirac point. So when we do these experiments, we start with Bose condensed atoms. The Bose condensed atoms, if they're at the start of the experiment, macroscopically occupy the lowest state of motion, which is the state that has 0 momentum. So it's basically just a uniform wave function of atoms. But what we want to do is we want to study band structure, and the interesting aspects of the band structure are often not at the very lowest energy, they're at somewhat higher energy, and maybe even in excited bands. So we need a method to take these Bose condensed atoms where they start and move them arbitrarily within band structure so that their behavior can probe the different aspects of the band structure. And here's our method for doing so. A first step we might take is to either put a force on our atoms to accelerate them, or equivalently have our atoms stay at rest and we just accelerate the lattice. In either case, we can cause atoms, and at this point, let's imagine that the lattice is off actually. So at this point, atoms would simply be promoted from some 0 momentum to some finite momentum. They would still remain in a momentum eigenstate, but they would just be boosted in a Galilean manner up to some finite velocity. Now what we do is we adiabatically ramp up the intensity of the lattice potential. And when we do that, it turns out that there's an exact 1-to-1 mapping between a momentum state and a band state. If we promote the atoms to a specific momentum state, for example, in this one-dimensional example shown here, then when we adiabatically ramp up the lattice,
the atoms will be promoted into the first, or the first band, I guess the second energy band, the first excited band, and they will be at a quasi-momentum which matches the momentum of the atoms, but when it's taken modulo the Brillouin zone. So the upshot of this is that by pushing on the atoms and then ramping up the lattice, we can put the atoms anywhere in band structure that we wish, in any band and at any quasi-momentum. Now, if we wish, we can accelerate the atoms or the lattice again. So we can move the atoms again, now in quasi-momentum space, but have them now move within the band structure of the lattice that has a non-zero intensity. And then finally, to see what's going on, we can at that point examine the atomic state, for example, probe its momentum distribution, or we can also use another trick, which is to adiabatically ramp down the lattice at the end. And now we sort of invert this mapping, and now every band and quasi-momentum maps onto a unique momentum state. So we can analyze in which bands the atoms have been placed. So we're going to use that method to study this interesting feature of the graphene's band structure, which is this Dirac point. So this is a place where two bands touch one another. There's a symmetry that prohibits there being an energy splitting at this location. And it's interesting to examine the states right around this Dirac point. So you can do so. For example, you can choose a basis where sort of a pseudo-spin basis where a particle trapped in site A of the unit cell is called spin up, and a particle trapped in site B of the unit cell is called spin down. And you find then that in the vicinity of this Dirac point, the Hamiltonian has this very simple form where the Hamiltonian is like that of a spin in an applied magnetic field, where that applied magnetic field increases in magnitude as you move away from the Dirac point, and it points in a direction, let's say, radially away from the Dirac point. So again, this is the basic structure of a Dirac point. And then the question is, how can we probe this Dirac point? In particular, we note that at the point itself, the Dirac point itself, there's a singularity in the ascription of states, right? So let's say we have at this point, we say, what are the eigenstates of the band structure at that location? Okay, so call this, field pointing in the y direction. That's pretty simple. It's a spin that either is pointing in the up y or minus y direction. And then similarly here, the states are the ones that correspond to a pseudo spin pointing either in the plus x or minus x direction. So the states are uniquely defined everywhere around the Dirac point, but at the Dirac point itself, there's a singularity in that definition. Which state you have really depends on how you approach the Dirac point. So how does one characterize that singularity? There's one method is to measure what's known as the Berry phase. So here we stay away from the Dirac point, but we say, let's take a state that is prepared in an eigenstate, and let's drag it in a circle around the Dirac point and see what phase it acquires. And in this case, because we're taking a spin 1/2 and dragging it around the equator, it should pick up a phase of exactly pi. This is something that's also been seen experimentally. So I'm referring here to experiments done in the Bloch group a number of years ago, where they take a Bose condensed gas of atoms, like in our experiment. They place the atoms in a superposition of two states, and then using some spin-dependent forces, they cause these wave packets to circle the Dirac point, so that one spin state goes one way around the Dirac point and the other spin state goes the other way around the Dirac point. And now they can close this interferometer by putting on another pi/2 pulse and measuring populations in these two spin states. And this is what they see. So let me point you over here. So what they're doing is they're opening an interferometer and closing it. And the closure is either done before or after engulfing one of these Dirac points. And if they close this interferometer before engulfing the Dirac point, they measure a Berry phase, which is 0. And if they close the interferometer after passing through the Dirac point, they measure a Berry phase of pi. So they very clearly see that there's sort of a singularity. There's, if you will, there's Berry flux, and it's entirely concentrated at the Dirac point, so that if you go around it, you pick up a factor of pi. So this is a beautiful demonstration of the singularity of the Dirac point. We've been playing around with a different approach that might have a more general application, which doesn't try to stay away from the Dirac point, but actually goes right to the heart of things. So here's the experiment we do. Let's say we have our atoms, we start them in their lowest band. So they're in, let's say, what is equivalent to a down pointing spin state in the language that I gave you. Now what we'll do is we'll displace these atoms and move them right onto the Dirac point. And then we'll hook a turn by some angle and pull them away from a Dirac point, also along a ray. And the prediction is that something untoward happens at the Dirac point. At the Dirac point, because you have a degeneracy of states, even no matter how slowly you're moving, you're no longer guaranteed to remain, let's say, just in the lowest band. There's no notion of adiabatic following in that case. What happens instead is that when you emerge from the Dirac point, you should now have undergone a coherent rotation in the space of states between the lower and upper bands. And in particular, the atoms will be hit by a pulse, which rotates their state by a polar angle theta, as a result of which, if we measure, let's say, the population of atoms in either the lower or the upper band, we'll see a characteristic variation with the rotation angle. And this factor of 2 is exactly the factor of 2 that turned the Berry phase from 2 pi to 1 pi. So measuring this, people relate it to like a Wilson loop operator, but measuring this state rotation or the variation in populations directly characterizes the singularity at the Dirac point just as much as a Berry phase experiment would. So here we do these experiments. We have our honeycomb lattice. We accelerate the lattice in this case so that the atoms go to the Dirac point and then go away from the Dirac point at some angle with respect to the entry ray. And then we do inverse band mapping. So when we look at these populations, these densities of atoms in our images, they're telling us what fraction of atoms is in different bands of the lattice. In order to interpret these measurements, we have to be mindful that the lattice is in the laboratory is in a moving frame. So we take account of that. And then finally, we obtain these band populations. And you see the signature we observe is really very clear. Let's say the population that remains in the ground band varies pretty much like cosine squared of theta over 2, which is what one would predict for a Dirac point. The data are not perfect because this is actually an experiment, but the fact that the data look so good is really a testament to how robust this feature is. This is a feature that's associated with a topology of a Dirac point, and here we probe it directly. So we have ideas for how to extend this to other band touchings as well, and also how to understand the effects of interactions on this band topology effect, and that's something that we're chewing on at present. So this is all well and good, but we also would like to expand the range of both quantum simulation and also all other applications of ultra-cold atoms. And one sure way to do that is to look in a part of our field where nothing grows yet. And specifically, what we noticed is that if you look at all the atoms that have been brought to quantum degeneracy so far, let's say using laser cooling, there's sort of two different kinds. There's all the ones here, which I've boxed in black boxes, which are atoms, either alkali earth atoms, or certain either full or half full shell atoms, for which the total orbital angular momentum of the electrons is 0. And what that means is that if I go back to the picture that Maxime offered for optical trapping and how optical forces are exerted on atoms, when you shine off resonance light onto an atom to place some kind of optical force on it, you are yanking on the electrons that surround the atom. And if those electrons lie in a perfectly spherical distribution, then it doesn't matter, what the polarization direction of the light is. The kind of interaction, the strength of interaction is going to be the same. And that means that you're lacking a real handle on how to put forces, optical forces on atoms in a way that depends on their internal state. In this case, their orbital angular momentum state. Now there are these other atoms which people have been laser cooling, lanthanide atoms. I saw Dima Butker was one of our participants. Dima's done a lot of the really essential spectroscopy on dysprosium, for example. And these lanthanide atoms are very anisotropic. They're great for this kind of physics. If you want to put a spin-dependent optical force on a lanthanide atom, go ahead, it'll work. But it also turns out that these lanthanide atoms are to some degree maybe too complex for some experiments in ultracold atom physics. In particular, if you have mixtures of different states of these atoms, such as you might want to in some kind of quantum information experiment, those spin states will often just relax due to magnetic dipolar interactions. So we looked at the periodic table and wondered whether there's other atoms that people haven't looked at yet, which both have the property of being anisotropic because they have orbital angular momentum in their ground state, but that also would be not very magnetic. And we came up with actually something like a dozen different transition metal elements that had not previously been recognized as candidates for laser cooling. So we think this is a really big deal. I think if we can introduce these atoms into the ultracold realm, a lot of interesting physics will follow, some of which I'll point to at the end of this talk. But certainly, I think new things will come out of it. So we have an experiment underway right now to try to laser cool titanium as the first example of carrying out this idea. Okay, next I want to move on to topics in quantum sensing. And here I'm going to talk about experiments that we do in the field of cavity quantum electrodynamics, where we take atoms and we place them inside of an optical cavity, a very high finesse optical cavity, and we try to study the interaction between atoms and single modes of a light field in order to extract some new physics. So here's kind of how that's rigged up. Here's our quantum system, which is our atoms. We place them inside of this high finesse cavity. And when an atom, let's say, emits light, it will preferentially emit light into the cavity. And that cavity photon preferentially, before skipping out of the cavity, will interact back with the atoms. So you end up with a very strong atom-light interaction, which is not terribly marred by spontaneous emission out of the cavity, either in a transverse direction or even out of the cavity mirrors. In this part of the talk, what we're using this setup for is actually as a quantum sensor. So the idea here is to get a quantum system to interact with a beam of light in a minimally destructive way, so that all of the information that the atoms are shedding through their optical interactions, that all of that information is placed into the cavity light, and then all of that information goes out of the cavity into our detector. So we think that this is the right setting in which to study what are the limitations of quantum measurement, and given that we can reach those limitations, what can we see that's new? So here's one application that we've been working on recently that I want to talk about. It has to do with making continuous real-time measurements on an atomic sample. And this is interesting for lots of reasons. I'll tell you that it's interesting from the viewpoint of studying things like thermodynamics. It's also critically essential for things like quantum information processing, where eventually we're going to be doing things like measure to diagnose errors and then do something. So we want to measure during the quantum or the ultra-cold evolution of an atomic gas. So what we're doing here is we're taking a gas of atoms and we're using a cavity just to count the number of atoms. A very, very simple measurement. We count the number by the fact that the resonance frequency of the cavity, due to the presence of atoms inside of the cavity, is shifted by some amount. So the resonance frequency shifts by an amount proportional to the atom number. So let's say with a lot of atoms initially in the cavity resonance has been shifted over very far to the left in this diagram. Okay, so we probe the cavity and we can see that there's very little light coming out of the cavity because we're probing a cavity that's with light that is off resonance. And now what we do is we affect evaporative cooling. So we put the atoms in a potential that has a lip. And the hottest atoms within this gas can escape over the lip. And when they do so, the number of atoms in the gas drops. And as that number drops, the cavity resonance shifts. And if we keep watching, we can see the cavity resonance match that of our laser beam and then go out of resonance with our laser beam. And so you can imagine that if we examine this trace of intensity as a function of time, we can use it as a proxy for measuring the atom number as a function of time. Okay, so we've refined this method a little bit. So now we actually use feedback to make this an experiment that has more sensitivity and higher dynamic range. Okay, so we basically have a laser beam that remains always at a fixed point with respect to the cavity resonance as the cavity resonance shifts. And if we measure the frequency of that laser beam, that's the same as measuring the number of atoms. And what we see is data like this. So this is like a single run of the experiment where about 2,000 atoms undergo evaporative cooling down to about 500 atoms. And we probe these atoms continually with our optical probe, albeit a very weak optical probe, one that only uses 6 picowatts of light. We record the atom number by this feedback method that I just told you, and this trace is a real-time record of the atom number during this process for a single shot of the experiment. If we probe with more light, we get data that is a little less noisy because the shot noise level is lower. We also heat up the atoms during evaporative cooling because they're interacting with light, so we lose more atoms along the way. And that's a little bit of the trade-off that we're studying here. We can conduct this experiment not just once, we can conduct it hundreds of times. And now we develop a really deep statistical ensemble where we get to examine both shot-to-shot variations, let's say in initial preparation of the atomic gas, but also even by looking at a single one of these traces, we can look at how much each trace varies with respect to kind of an average behavior that we would have expected. So we can start looking not just how average quantities vary in this thermodynamics process, but also how the fluctuations evolve. I talk about evaporation as a thermodynamic process. It's rather a non-equilibrium thermodynamics process. So we can think about evaporative cooling as something like this. We have a trap with a certain depth. And then when atoms, by chance collide and one atom emerges with a very high energy, it can leave the trap and by going over this evaporation threshold and disappearing. So clearly we should be able to write down theories that would tell us what is the average rate, let's say, at which atoms are evaporated out of the trap as a function of things related to their thermodynamics and their interactions. But we can go a step further now that we're actually looking at real-time records. We can ask these theories not just to reproduce what is the average flux of atoms in a certain thermodynamic starting point, but also what the fluctuations are, right? So if at some point in the evaporation process, we've sort of in a binomial way divided between atoms that are trapped and atoms that are no longer trapped. And somehow that division should also come along with statistical fluctuations. Those fluctuations are also subject to further dynamics. So these are things that we can study in our experiment. And I don't have time to go in detail into this. I'll just focus you on these data down here, where what we examine is the variance in the atomic number that we see at a late time, conditioned on the number of atoms we see at an early time. So, one sample might come in with few atoms, another one with more atoms. So we want to take that kind of fluctuation out of the variation in the final state, but rather say if all the samples had entered this experiment with exactly the same atom number, how much variation would there be in the atom number at some later time? So that's really getting to the heart of fluctuations that are seen in mesoscopic systems when they're undergoing thermodynamics. And so our data are showing us that the noise or the fluctuation level we see is roughly equal to what we would expect given binomial noise, which is something we're trying to understand. We might have expected larger fluctuations in some settings and smaller fluctuations in other settings. And here's where the CIQC is helping us and connecting us with Joel Moore's group so we can study this question further and turn these experiments into like a broader survey of quantum transport and quantum thermodynamics questions. Let me now turn to another topic in quantum sensing, which is quantum sensing, but where now the sensing medium is actually the atoms. We're going to use the atoms to study something else. And in particular, we're going to use even single atoms to study something. In this case, we're going to study optical fields. Okay, so I should just point out, here's the group that works on this. And then baby Claire here, she is part of a very aggressive youth outreach program. We're really reaching down into the early grades to teach quantum mechanics to young kids. Okay, we're going to use atoms as a scanning probe microscope. So again, I can turn to my colleagues here at Berkeley and see plenty of examples of scanning probe microscopy that is absolutely essential for all sorts of material science. So for example, in an STM, a scanning tunneling microscope, you run current between a tip and a sample, and you measure that current as your tip is scanned across the sample. And you can then measure features of your sample with really high spatial resolution. And then one takeaway I want to take from this STM approach is that there's sort of two different ways of taking these scans. One is just to drag the tip across the surface at a constant height and see how much the current varies. And another one is to use feedback to keep the tip so that there's always a constant current running across it. And that turns out to be a measurement, if you will, of the height variations of your sample that you're studying. So we'll come back to that idea in a second. But the question we sort of pose here is whether anything is to be gained by replacing this tip, which is kind of a chunk of metal in this case, down to just a single atom. And why would that be useful? It's kind of a quantum sensing question. One of them would be that a single atom is something that is absolutely calibrated. Its response to anything you do to it is simply given by fundamental constants, and every atom is the same. So you would have a perfectly calibrated sensor. You would be able to use fancy techniques to measure the state of the atom. And most appealingly, at some point, you could also use things like entanglement between, let's say, several tips in order to make really new types of measurements with a scanning probe microscope. The idea of using a single atom sensor within something like a scanning probe microscope is not entirely new. So I'm familiar, let's say, with Amir Yacobi's group, where they put a single NV center down at the bottom of a atomic force microscope tip, and they use it as a single atom magnetic sensor, or maybe a strain sensor, I'm not sure what they use it for, dragging across the surface. Anyhow, here we want to get away from the complications of working with materials and work with something even more pristine, which is just a single atom. And so for that, we need a single atom. And here's how we prepare a single atom. This is not a technique that we've pioneered. This has been pioneered by several groups and now really perfected by Antoine Brouet's group in Paris, and then also the group at Harvard. And I should also give credit to Mark Safman's group at Wisconsin for doing a lot of the early work here. But here's what we do. We take off-resonance light, which can be used to trap an atom. We run it through an acousto-optical deflector, just something we buy off the shelf, which we drive with a sequence or a comb of different radio frequencies. And then we run the light that comes out through a lens. And what happens is that for each radio frequency here, we get a separate little tweezer trap where the light is trapped very, very tightly. We load atoms into these traps, but we don't really control how many atoms go into the trap. It could be 10, it could be 55, who knows? We're not really that good at controlling it to begin with. But now what we do is we apply laser cooling light. And under the application of laser cooling, it turns out, this is a beautiful discovery, that atoms are ejected from the tweezer trap, but they're lost in pairs. So if you're left with a single atom in the tweezer trap, that's a stable configuration. It can just remain laser cooled for as long as you want. If you're left with two atoms in a tweezer, that's an unstable configuration. Laser cooling will cause these atoms to collapse into a molecular state and emit a lot of energy, and then both atoms are lost. So the end result is that essentially, depending on the parity of the number that you initially loaded into the trap, you end up with a trap that either contains 0 atoms or that contains 1 atom. And now that it's been reduced to 0 or 1, it will just keep fluorescing ad infinitum. And here's an image that is taken in our lab with like I think it's a half-second exposure. So these atoms are really glowing for a really long time, so that it's really easy to take images and see which of these traps holds a single atom and which doesn't. These are data that give you a sense of the measurement fidelity in this process. I mean, you can see by eye that there's no mistaking an atom for not an atom, but just in case you don't believe me, when we take repeated images of our tweezer array, we can look at let's say the 10th image, and if we see an atom in the 10th image, we can say what was the intensity that we saw in the 9th image. So that means we're looking at a trap that definitely had an atom in it. On the other hand, if in the 9th image we see no atom, then in the 10th image we can look in this region and we know that it's a non-atom event, and that's this histogram over here. And you see that these two situations are extremely well discriminated one from the other. So this is potentially a very high fidelity way of measuring the presence. And if you can turn presence into a state sensitive measurement, that would be measuring the state of an atom with this kind of fidelity. This is all toward an experiment that we're building, which I'd like to mention now, but we'll talk about just a little bit later, which is to take a bunch of these tweezed atoms and place them inside of a high finesse cavity. And again, as I mentioned earlier, within this high finesse cavity, we can ask atoms to interact with each other via the cavity field. For the purpose of what I'm going to study right here, we're asking ourselves the question of, inside of this cavity, what is the spatial pattern of the light? So inside of this cavity, which we can drive either with light at 1560 nanometers, which we use for trapping atoms, or at 780 nanometers, which we use for interacting with the atoms. Inside of this cavity, there's a spatial variation of intensity. There's sort of a standing wave mode of light inside of the cavity. And we want to know what is its radial profile and what is its axial profile. And the way we do that is we pay attention in this graph, not to the existence of an atom, but to the actual amount of scattered light that we see. So we're looking at the brightness in each of these images, and we see that the brightness varies in a well-determined way. Let's say if we just have an atom in a tweezer, but there's no other light field present, we see that the brightness is low when we're using far-off resonance light for laser cooling. That's what we expect. And it's bright if we use near resonance for laser cooling. Now we place the atom inside of a cavity that also contains light, and we put the atoms at a location where there's a significant amount of local intensity. And what we see is that this entire curve is shifted for the reason that the light that the atom experiences, or that the atom is sampling, is shifting the resonance frequency of the atomic transition. So by measuring this shift, if you will, at constant current or constant intensity, we get a measure here by comparing this frequency with that frequency. We get a measurement of the how much the atomic energy levels have been shifted in frequency, which then is something that directly tells you what was the intensity of light where the atoms are located. So here's the proof in the pudding. We take tweezers, either of atoms that sample the middle of the cavity, where they see a significant variation of intensity, or some tweezers that as kind of fiducial markers are placed outside the cavity, and we see very little variation in intensity. And from that, we know that we're able to measure the intensity pattern of light inside of the cavity with really minimal absorption of light inside of a cavity, and with a spatial resolution that is at this point 100 nanometers. So this is pointing us toward an interesting application of cold atoms, and certainly of tweezed atoms, is to use them as sensors of local conditions that they experience. Now, let me move on to the last topic, which is the relation between what we're doing and quantum information processing. I presented a few different kinds of platforms. I talked about atoms that can be held in optical lattices. I talked a little bit about atoms held in optical tweezer traps. And I talked a little bit about atoms that are placed inside of optical cavities. How do atoms interact with one another in order to, let's say, do something like realize quantum gates? Okay, let's start with the Rydberg situation. The idea here is that your atoms that are held at a few microns separation can be transiently excited up to a Rydberg level. They interact with very strong interactions so that a gate can be affected in some time less than a microsecond. The interaction is fairly short range, so atoms have to be within 1 or 2 tweezers distant. And the coherence in this system, based on the lifetime of the Rydberg level, is that you should probably be able to realize maybe 100 gates before the thing falls apart. The atoms in optical lattices are different. Here we end up relying just on ground state atoms that overlap in a single trap and interact with one another. The interaction energies are very small, so the gates are very slow. They take milliseconds. But we do have the advantage that the coherence is very long, so we can affect very many gates before something untoward happens. In the case of atoms inside of an optical cavity, it's possible for atoms to have a spin-spin interaction by exchanging cavity photons in a programmed way. This would also be a very fast gate. It wouldn't have the same limitations on range because any 2 atoms inside of the same cavity would interact with each other. But it has the downside that, at least in the optical domain, the number of gates that you can realize coherently is pretty small. So I would say, in terms of an outlook where we should use these different kinds of platforms, the Rydberg systems are really standing out as a quantum simulation tool for spin models. There was a talk last Friday given by folks in the Harvard group that was almost brought me to tears. It was so beautiful looking at spin liquids. And definitely there's a lot of wind in the sails of moving toward quantum computing. Atoms and optical lattices are probably going to have to respond to this challenge by specializing in quantum simulations of itinerant particles, bosons and fermions. But there's also an approach to quantum computing that I want us to investigate. And then atoms in optical cavities, I think their specialization is going to be studying specifically what quantum systems do when they're open, when they're subject to measurement, also subject to feedback. That's kind of the applications I see for these different platforms. And I'll just mention that through the CIQC, we're building up a Rydberg tweezer apparatus at Berkeley as well, but we're also collaborating with several CIQC investigators, including Manuel Endres down at Caltech. Okay, so I'm running quickly out of time, but I do want to spend time on this outlook. I was asked if I was to assign somebody to work on something important, what would it be? For me, first and foremost, I would like people to solve my engineering problems. This is what my cold atom experiment looks like. And this is what a functional device looks like. And the question is, how do I go from this, which is optics hardware, lots of steel, UHV chambers, high currents, just a big old mess, to something that is as rigorous and miniaturized and reliable, and using feedback as something like a chip. So I don't have time to go through all this, but certainly groups that could specialize in how to produce ultra high vacuum quickly and in a wide variety of settings. People that could improve the optics setup enormously could help us enormously. There's a lot of work to do with atom detection. Every revolution in detection leads to a revolution in science. And then there's a lot of difficulty that we have just in how to control a really complex apparatus, where I can imagine that some of the experts in the CIQC could really help us. Another topic I would like people to work on for me is to understand deeply what do many-body quantum systems do when they're subject to feedback. So let's say in our atoms and tweezers experiment, I don't have time to explain this, but if we shine light on our atoms, we can cause specific atoms within this tweezed array to interact with one another. Almost a completely programmable quantum system. But at the same time, the atoms can also leak light into a detector, which sounds like a quantum system that collapses. But does it really? Because the information that we gather here with maybe very high fidelity can be used as feedback to change what the atoms are doing. So this, on one hand, is something akin to error correction. On the other hand, it's asking a fundamental question about non-equilibrium quantum physics, which is, what is the physics of many-body systems when they are placed within a feedback system? And I think that's a very interesting question to examine. A third thing is, and this is where I'll stop, is how to realize a very fast and high fidelity readout of atoms. If we can do that, then we can jump very far forward. So let me describe an experiment that's already been done that we would like to do a lot better. Let's say we work with the optical atoms and we get into a mod insulator state, one where there's exactly 1 atom per lattice site. I can create a very useful state out of that known as a cluster state. And here's how it's done. You put a pi over 2 pulse so that every atom is now in the superposition of 2 spin states. You apply a spin-dependent force, like a spin-dependent lattice. Titanium would be perfect for this because it has very strong spin-dependent interactions with light. And you drag the atoms over so that they all sit over their neighbors, or their next neighbors, or the next neighbors. You can do all sorts of things. While the atoms are hanging out there, you let them interact locally until, let's say, a pi phase is picked up. And then you undo the state-dependent translation. What you've created is a cluster state where every atom is now entangled with its neighbor. What I showed was how to make a one-dimensional cluster state, but repeating that displacement in different directions would give a two-dimensional cluster state. This cluster state experiment was done very early on in the physics of cold atoms, back in 2003. A cluster state is a universal resource for quantum computing, but you need to do fast site-selective readout and then feedback from that readout to do something to the next atom. And so if we can realize very fast readout, I think we already have, even though an optical lattice is a very slow quantum computer, the fact that it places gates everywhere all at once is something we can leverage. I want to just finish with this slide. The Challenge Institute for Quantum Computing brings together scientists from a wide range of disciplines. The Center for Quantum Coherent Science, which is sort of the Berkeley Quantum Initiative, is meant to be even more expansive and to bring in, at least at Berkeley, everybody who thinks h-bar isn't 0. And with this wide range of expertise, what we should do is talk to each other a lot. And what I'm experiencing already personally is just since engaging in this center, I am stretched to learn all sorts of new things about engineering, about math, talking yesterday to Lynn, about theoretical computer science, attending the Simon seminars. I'm learning an enormous deal. I'm synthesizing new ideas, and it's going to allow me to make my science much deeper, sophisticated, and impactful. Another element I see here is what Nathan Wiebe has called a chain of respect. So, I don't expect a person who is doing electrical engineering, let's say, to, I don't know, directly do a computational chemistry problem. Maybe they will actually. But what I see is that we will all see, like in these links of the chain, and by knowing what everybody else is doing, we'll see the point. We'll see why what you're doing is important, what I'm doing is important, what she's doing is important, and so forth. And then finally, I see here an enormous opportunity for our students and postdocs to not be trained in a small silo, in fact, so small that it's a single research group, but really have a chance to mill around and meet people from all across the spectrum of science. And that will give them the capability to engage in this kind of multidisciplinary research and excel at it in the future. So let me just finish. Here's my group photo again. And I also wanted to highlight and give my extreme thanks to the staff that is really making an enormous difference in how the CIQC and then also the CQCS are operating. So many of you hopefully have met Carolyn Remick, who's our executive director. And maybe you've also had a chance to meet Sarah, who's helping us with innumerable administrative tasks. And we'll be seeing a lot of them in the days to come. So let me finish there. Thanks, everybody.
Thank you, Dan. Should I moderate the question?
Sure. Yeah. Yeah. Or I guess anybody who has feels a hankering to I moderate can moderate.
Okay.
And let me especially emphasize, students and postdocs, please, ask questions. But yeah, go ahead.
Norman, maybe brief me out about the difference between the question now and the question that we will have later personally with Dan.
Yeah, I think there seem to be some questions from the talk, so maybe we can start asking just a couple of those if people have them. And then I think it would be nice, Dan already touched on a lot of these big picture topics, but I think it'd be nice to open the floor to sort of, broader sort of discussions across the various fields that are at the colloquium.
So we have one question in the chat from Boubacar Conte. How many elements in the lattice are needed to guarantee the existence of the Dirac point?
That's I don't have a clear answer there. Yeah, so I mean, if we put periodic boundary conditions on a system, then of course band structure becomes discretized. I think you would still imagine you have the same set of states, but now they're sitting on a discrete grid, and I don't. So you don't end up with the same sense of a singularity at that point, I think, because you're jumping discontinuously anyhow from one state to another. So I don't think you have, but I think you must be sort of coarse graining the singularity there. But you're probably thinking to yourself, okay, well, I'm going to stick a bunch of optical components in a grid, and I want to study the same physics in order to I don't know, make a light at a Dirac point or something, right?
Yeah, we are doing a similar experiment actually, and I was wondering what the influence of the boundary was on that point. So, for instance, if the lattice is too small, are you lifting the degeneracy at the gamma point or at the center of the Riemann zone, or I mean, what is the exact consequence of the boundary? So that was the question, in fact. Is there a minimum size?
I mean, the Dirac point is one where let's see, it's somebody can help me out here. It's probably something like a time invariance or time reversal or parity or something, which determines that the two states at the Dirac point must be at exactly the same energy. And so, so for example, to lift that degeneracy, I would change the energy of the A and B sites so that they're slightly different. That would introduce a mass term, as they say, but it would kind of split those energy levels from one another. So I think actually the degeneracy at that location is probably pretty robust. I mean, I can imagine there might be something weird like, an even or odd number of lattice sites. There might be a difference there. But yeah, I think it's a fairly robust feature.
Okay, thank you. Thank you, Dan.
Hi, Dan. I had a quick question. So you spoke about this the simulation at the end with contrasting Rydberg atoms and neutral atoms. So is there it wasn't? Can you speak a little bit to the programmability aspect? So how would you actually program the different simulations using the same gas of neutral atoms?
Yeah, right. So let's start with like a Rydberg simulator. I mean, in a Rydberg system, you have a bunch of tweezer traps. You have some programmability in the sense of where you locate them. So you can make interactions probably stronger and weaker. And there's also some variation you get with the relative angle between the two states. But I would say to get into the most programmable situation, what you would do is you would make gates happen between specific neighboring atoms and not to anybody else. And the two ways in which you would do that is, let's say with your microscope objective, which sends light in, you would also send in your Rydberg excitation light, which is what we'd like to do at Berkeley. And then you basically activate these out. What you're doing with the Rydberg excitations, you're taking boring neutral atoms and you activate them. You can selectively activate two of them so that they interact, and then deactivate them and nobody else paid any attention. So that would be complete. The other way people are thinking about doing this is by using light from above, maybe just to shift atoms into a resonance where everything is interacting, and then out of a resonance. That would also be sufficient. So there, basically, you can do everything. To get gates at long distance, I don't see it. I think you would probably have to like physically drag the atom or something, and I'm not sure that that's compatible with the timescales of the experiment. So I think it probably would be kind of local interactions that you're working with, not surprisingly. In a optical lattice simulator, there are people, I think we'd also be interested in going in this direction, that would want to make a very what we're doing with the optical. So there, I guess I can imagine, you bring an atom next to its neighbor, it interacts, you bring it back. Like that would be, so you could probably use tweezers again to move atoms or something to make that interaction site selective. But I think the the lattice approach has such a terrible strike against it in terms of the interaction time. The time scale. I mean, you guys are really scaring me, when I hear that we're talking about 10 to the 15 gates or something to fix the nitrogen problem. It's like, I don't want to wait 10 to the 15 times a millisecond. That's not for me. But so instead, I think there we have to think about being really selective. And I think the selective thing is to do gates everywhere all at once, so that the gate, which is very slow, can just be taken care of in one step, and then find a way to make the measurement ever faster. Make it sub microsecond, and just make measurements and go in a cluster state approach.
Yeah, so I guess that was getting at the issue that I was trying to understand. So in the Rydberg case, I understand that you can vary the interaction, so that gives you a sort of a way to a handle to get programmability in. So in the neutral atom case, I just don't understand what is going to give you that so in other words, what I'm missing is I didn't quite follow what are the interactions available and to what extent you can program them, or say, well, we have two different kinds or many different kinds of interactions, and we'll do either pattern A or pattern B.
Okay, so again, well, certainly it's very easy to do parallel gates on an entire lattice. It's like at base, it's kind of a spatially invariant system. So if I want to do this kind of cluster state, I have an n by n lattice, and I do 2 shifts, and then we're done. We're done with the shifts completely. You can be more programmed than that, I think, if you really wanted to. I think you should be able to get just 2 atoms at neighboring wells to interact and nobody else to pay attention. That should be doable. I think that's a programming method that I know the block group in Garching is working toward. So I think it's super doable. But in terms of like running a quantum computer, I just think like you have this shackle on your leg, which takes a millisecond. I think you're just never going to get to. I used to be much more sanguine about it, but I think when I saw this 10 to the 12 or 15 gate thing, I was like, nah, you're never going to catch up. But I do think so. Okay, but there's other applications. There's a lot on the way. If you wanted to a programmable quantum annealer, I think if you had a really arbitrary sort of interaction landscape, might be a pretty powerful tool. And then something like this cluster state approach, I think should not be dismissed. And again, it's not clear to me that I know we can think about methods. You could say, well, cluster state, that's great, Dan, whatever. I get my 1,000 by 1,000 or something array of neutral atoms. Okay, so I get to work with it, but how do I get to the really large number? And so there, I think right? Because you just keep adding more rows to your cluster state, and or columns, and I think that's doable. I think you can just keep loading more and more atoms on an edge and translate and just keep adding more. I don't see that there's a fundamental problem. It's just hard, but it's doable.
Dan, maybe just following up on Umesh's comment. So, I mean, I think this is what you were alluding to, but there's kind of, this idea of using a quantum gas microscope, of course, to sort of make this kind of optical lattice quantum computer. And your sense is that that isn't quite as promising. I mean, could you imagine sort of, instead of doing sort of one gate at a time and then waiting, just doing like, sort of like your cluster state thing, but where you kind of do, pairs, all pairs of gates by turning off half the atoms and then another sort of set of all pairs of gates. I think that's what people were sort of at least talking about in this gas microscope quantum computer. But is your sense that that's just, having worked on related stuff, that you think this sort of generically this gas microscope approach to quantum computing is not the right way to go?
You're asking me?
Yeah.
Yeah, I don't know about right way to go. I mean, if you wanted, what are you aiming for? Are you aiming to beat the state of the art, like a 200 qubit machine with 200 gates? Okay, you could probably do it. I mean, 200 times a millisecond? I can wait that long, so that's fine. That's fine. And to realize, the basic primitives of like error correction and such, why not? I think you can do that. If I'm trying to, like in the sense of Matthias Treuer's talk from a few weeks ago, if I'm trying to use a quantum algorithm to solve a problem that is important to people, like, I don't know, breaking codes or something, I just think you're up against such an enormous barrier.
Sorry, just to follow up a little bit, going back, just to clarify, I didn't mean doing this to do quantum computing per se. I was just going back to simulation.
Yeah.
And I was saying, look, even when you're doing simulation, you want to be able to program, right? To say, well, on this same substrate, I want to simulate this system or that system, as opposed to creating the system, actually creating a system to do a particular simulation, right? So that's what I was getting at.
Well, I think that there's a way forward. That's a really interesting idea. So let's say, like in a computer, I wanted to simulate a triangular lattice, right? I still have a square grid of data,
yeah.
But of course, I connect things in a way that it looks like a triangular lattice, right? It just has to do with what couples to what. And so in this example that I gave, where you could imagine translating over by one site, by two sites, you can translate in a knight's move, you could do all sorts of things. Then I think you probably could put in sort of a trotterized approach. You could put in a fairly arbitrary lattice. So I think maybe it does have some real legs to it.
Okay, we have maybe a few minutes still, and a question from Sarah Mouradian. What are the challenges in cooling those new transition metal atomic species? And I would add, generally, when you tackle a new atom, what are the challenges? Not only for your experiment, but you think generally speaking.
Okay, so I guess a basic challenge is to find a scheme that doesn't require 80,000 lasers. You want something which, where with a really sparing use of laser light, you can maintain an atom in a particular two-level system for laser cooling, not try to patch up too many other states into which the atoms might fall out and have to be repumped. So you look for an atom that has some kind of simplifying structure where you think there's a transition that is essentially closed, that when you excite the atom, it always comes back to the same initial state. With only very few exceptions, and then you're really at a good starting point. So that's what led us to look at these transition metals, and we think the specific ones that we've identified, we actually know what the transition is for all of them, and I think any of them could be laser cooled based on what we see. From there, your next challenge is you have a bunch of lasers, and you have to generate laser light. So I guess I could just call up Boubacar and say, give me this and that, and he'll do it. But anyhow, I'm not quite sure. Okay, so that's a little bit of work. So with titanium, I don't know, we're talking about like 6 or so colors of light that are needed, some for pumping atoms up to a state where they can be laser cooled, and other stuff for bringing it back down to a state where they can sit in a lattice. So that has to be figured out. And then the next thing, I mean, what we're struggling with right now is really mundane. It's high temperature chemistry. Making an atomic beam of rubidium involves heating rubidium up to 100 or 200 Celsius. And making an atomic beam of titanium involves heating titanium up to about 1400 Celsius. And then working later with ruthenium that we're talking about, that would be more like, I don't know, 1800 or 2000 Celsius. So now you've got like, you know, high temperature stuff. You've got, anyhow, it's just about producing an atomic beam. So you just have to learn to do it. It's not super fundamental. I think it's all been, you know, people have done molecular beam epitaxy with just about everything. So people have found solutions that work for everything. You just have to learn what those techniques are.
Like maybe on that note, since I'd rather not cut the student postdoc discussion short, I think there are some questions still in the chat, but I think they're from students and postdocs, so it's actually good. But let me ask, except for Dan, let me ask PIs to sort of step out, and let's give students